This video is explaining the transformation dilation. Dilation is another word for shrink or enlarge. Shrink, or it could enlarge. Shrinking gets smaller, enlarging gets bigger. So if thinking about my hand, I can shrink it or I can make it go back to bigger. Shrink or enlarge. Think about dilating. Your eyes can dilate when you're waking up in the morning. Your pupils are bigger so you can let in light. So when the light turns on, your pupils will actually start to go smaller because you don't need to let in as much light. So then when it goes back to dark, your pupils need to get bigger so you can actually get more light so you can see better. When you dilate, there is a change in position. Because as it changes, part of it could get smaller or it could get bigger. So part of it actually it does move. It will move. But there is no change in orientation. No change in orientation. It might be hard to understand with my fingers, but you see how these fingers are still pointing up, and then my thumb is still on the left-hand side. As it gets bigger, it's still going in the same direction, pointing the same direction. Even though my thumb, as it gets smaller, it goes inside, but my thumb is still on this side and pointing this way. If it's shrinking and enlarging, then the size will not be the same. The shape is still the same, but it's no longer the same size. That means that the figures are not isometric. So of the four transformations, dilations are the only ones that are not isometric. Now, there are a couple of things about dilations that we need to remember. The first one is that dilations, yes, it's pronounced dilation, not dilation. There's no extra A. Dilation is centered at a point, which in most cases for the rules, it'll be at 0, 0, the origin. You can change it to be centered at another point, but you have to do composite transformations to be able to do that. We have what's called a scale factor. Not a scale, but a scale factor. Scale is when you make sure you're counting by something. A scale factor is what you multiply or divide your values by to make it get bigger or smaller. So scale factor we're going to call K. To determine your scale factor of K, you actually take the image coordinates and divide it by your pre-image coordinates. So you could do x prime over x because image is prime, pre-image is not. And it should equal to the same thing as your y prime over your y because you have to actually do the same scale factor to the x's and to the y's. You can't do one of them to the x and a completely different one to the y. To know if you're going to enlarge or shrink based off of your scale factor, if your K value is bigger than 1, you're going to enlarge it because to keep it the same, you're going to multiply by 1. So if it gets bigger than 1, it'll get bigger. The numbers get bigger. Now, that could also be a fraction. An improper fraction would give you an enlargement. To shrink, K has to be smaller than 1, so it'll get smaller, so a fraction as well. But you have to be bigger than 0. You can't multiply by 0 because then it will literally go away. But you also can't multiply by a negative number because that actually changes it into a completely different transformation. If you multiply by a negative number, you could be rotating it or reflecting it at the same time. And we only want to talk about dilation at the moment. So dilation, you can only multiply by positive numbers. Dilations are only positive numbers. And it's smaller than 1, any regular fraction, any proper fraction, would be a shrink. Any improper fraction would be an enlargement. If it's a 1, it doesn't do anything because it stays the same. So the description is to dilate. You're going to, again, it was talking about multiplying or dividing. You're going to multiply your scale factor, which is k, to all of your x and y values. Now, we're not going to use division because technically if you multiply by a fraction, that is division. Multiplying by a fraction is division. There is also fancy terminology that you might see for dilation because it's multiplying instead of having a rule of negating and flipping things. Just like with translations, you had horizontal and vertical components. Well, in dilations, the fancy terminology would be called a size transformation. Size transformation. And again, the reason why, if you think about it, you're changing the size. The size changes with dilations. It's a size transformation of magnitude. Magnitude tells you what size you're doing. Magnitude k. Because it'll tell you to size transformation, you're multiplying by your scale factor. This is just the fancy terminology of saying multiply by k. So you're dilating by k. So it'll always be size transformation because you're dilating, that means dilation. Magnitude k, that means your scale factor of k. That's just the fancy terminology. The algebraic method, algebraically, again, this is your rule, your mapping rule. Because it doesn't have very specific ones like reflections and rotations do, we have the one your pre-image maps to. We're going to figure out what to do to get our image. In order to get your image, you multiply whatever your scale factor, which was k. You do k times your x's, all of your x's, comma, and then you do the same exact k value times your y values. Now, again, just like with translations, this blue k actually needs to turn into a number. So if you just put kx, that is not correct. You actually have to put the actual value on a problem. So, for example, if the question says to dilate by 3, the rule here would be our pre-image xy maps to, dilate by 3 means multiply, so it would be 3x, 3 times x, comma, 3 times y. And then we would actually do that multiplication. So you don't just put the letter k, you actually put the number for the k. So graphic representation, again, I'm going to give the pre-image coordinates. So point A is at coordinate -2, -1. Point B is at coordinate -1, 2. And point C is at 1, 1. We do have an x and y and a scale. So not scale factor, but we have a scale. So we can graph this. So -2, -1 is A. B is at -1, +2. And C is at 1, 1. Go ahead and connect your coordinates. If I were to dilate, my center of dilation should be 0, 0. Because if I follow this rule, then my dilation is at 0, 0. The thing is that when you dilate, it does change position, but it does not mean that your pre-image will sit in the middle of your image. That's not what's going to happen. I'm going to give the image coordinates, and we're going to see what happens. A prime is at -4, -2. B prime is at coordinate -2, 4. And C prime is at 2, 2. So we have -4, -2 is A prime. -2, +4 is at B prime. And 2, +2 is C prime. Do not curve your lines to make it go around. You'd still want to make this a triangle by connecting your coordinates. So even if it goes through, that's okay. If I've given the coordinates, and I think this is a dilation because as you can see it has gotten bigger, but we've got to see if it's a true dilation or not, which we can prove it. We're going to talk about proving it with our property. But I actually want to see if what our scale factor is. From the pre-image to our image, it did get bigger, so it should be an enlargement. So if we want to find our K value, we will do our image over pre-image. So if we take our A prime and A, we can try that. So we would have our X value for our A prime, for our image, is -4 over our pre-image was -2 equals. This should equal the same thing with our Y values, so we got to check that. So -2 for our Y divided by a -1 for our Y. -4 divided by -2 is a +2, and -2 divided by -1 is also a +2. This is larger than 1, it's positive, so it should have enlarged by 2. Now we do want to check, and we'll just check this quickly. -2 divided by -1 is 2. 4 divided by 2 is also 2. So far B prime and B are good. We have to check C. 2 divided by 1 is 2, and 2 divided by 1 is also 2. So all of them from A, B, C to A prime, B prime, C prime is multiplied by 2. So that is in fact a dilation. So in words we would say dilate by 2. And our rule would be x, y maps to 2x, 2y. Now, the property down here will actually prove, in fact, that this is a dilation. We can see that all of our scale factors are the same, so this should be a dilation, and this will actually help us prove it. Properties are helping you prove it. The segments of the pre-image, so A to B, B to C, and C to A, are parallel to the image segments. That's the first part. That's the first thing we need to see. So AB is parallel to A prime, B prime. BC is parallel to B prime, C prime. And AC is parallel to A prime, C prime. We can check that by, for parallel, we would use slope. So up 2, right 3. That's 2 over 3. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. 4 over 6 is also 2 over 3. So we can see that these are in fact parallel. And if we did the same, we would show that B prime, C prime, and BC are also parallel using slopes. And these two lines are parallel using slopes. Then the second thing that you have to show is that A prime, segment A prime, segment B prime, and segment C prime all pass through the center of dilation. And since we were able to find a rule, the center of dilation should be 0, 0. So if we were to connect these coordinates, and you can actually do this mathematically, but if you were just to connect these coordinates, so B prime to B crosses through 0, 0. C prime C crosses through 0, 0. And A prime A crosses through 0, 0. This is also called a point of concurrency. All of these lines would cross through this one point. So if it goes through the center of 0, 0, this is the center of dilation. So this is in fact a true dilation because the A prime, B prime, and AB, all the image segments and pre-image segments are parallel, and then all of the connectors are going through the center of dilation. So that is correct. You can also show this by finding the line, the actual equation of this line, by doing your slope. You have your two coordinates, finding your slope, and then finding your y-intercept. You have to make sure that the y-intercept are all 0, 0 for all three of these lines. You would show that they are 0, 0 to show that it does go through the origin. That's how you actually prove it is a dilation, by using this property.